In this lesson of 7.5, we're going to continue to look at quadrilaterals. And specifically in this lesson, we look at trapezoids and kites, two more specific types of quadrilaterals. So the first one we're going to look at is trapezoids. Many times we can be very familiar with trapezoids. You should have learned that back in earlier forms of geometry in elementary. But a trapezoid that we typically think of is more of an isosceles trapezoid, which is the second one, where they're congruent on both sides. But a trapezoid is any quadrilateral that only has one pair of parallel sides. So if you think back to what we've been covering, we've been talking about parallelograms that have both parallel sides, both sets are parallel. But in a trapezoid, just one set has to be. Then those parallel sides, we consider those parallel sides to be called the bases of our trapezoid. And this terminology is going to be important because especially when we talk about the base angles, and we talk about how to find, later on we'll talk about the mid-segment, we're going to talk about area and all that stuff. You have to be able to know what the bases are in your trapezoid. So when we talk about bases, we're also going to be talking about base angles. Base angles are going to be the two angles that come off the same base, that same side base. Okay? The other sides are called legs. So we have two legs. Those are the sides that are not parallel. And then we have our base and our base angles. The base angles have to be the ones that are on the same base, as it shows here with our arrows. And then, like I said, further down here, it talks about isosceles trapezoids. Isosceles trapezoids, like I said, are the ones that we typically think about. Just like an isosceles triangle that has two sides that are going to be congruent, an isosceles trapezoid has both legs of the trapezoid are going to be congruent as well. So let's look at some of our theorems that we have for trapezoids. So these theorems all focus on it being an isosceles. Okay, so that's one key thing to note on for these ones. So an isosceles trapezoid, the first theorem tells us base angles theorem, and it essentially just tells us that the angles, those base angles, the ones that are on the same base, okay, they are going to be congruent with each other. Okay, so AD in this case here is going to be one base, and if you notice, our angles are the same on both sides. BC is our other base. The angles are the same. They both have one line. And so as it says it over here, it shows us A is going to be congruent with D, B is going to be congruent with C. Our next theorem, base angles converse, this one tells us just the opposite. Remember converse, it flips it around. So it tells us if we know that a pair of base angles are going to be congruent, then it follows that we know that the trapezoid is going to be isosceles. It's going to have those two legs that are the same. So this would have been a way where if it had drawn our trapezoid with just the base angles and had just marked those, if this was all I was given, then I would be able to add the tick marks to say, okay, well I know it has to be an isosceles because those base angles are congruent with each other. And then our last one focuses on diagonals. Okay, remember diagonals connect our vertices that are not consecutive. They're going to be across from each other. Diagonals go through. They're like a cut across. They go through our shape. And so our isosceles trapezoid diagonals theorem, it tells us that if it is isosceles, then its diagonals are going to be the same size. They're going to be congruent. So in this picture, I can mark each of these diagonals with two marks because they're going to be congruent with each other. So if we look at this example that we have, let's first talk about this trapezoid. It tells us it's an isosceles. And so first think about what our bases are going to be. Okay, bases are going to be the ones that are on our parallel sides. So I have a base up here of KL. I'm just going to mark it with a B1. It's my first base. And then I have JM as well. I'm going to call it my B2. Okay, I have two bases, KL and JM, because they are my parallel set of sides. And it asks us to find the measure of angle K first. So let's look at it first. So on our base, we said when we have an isosceles trapezoid, if we go back, if our trapezoid is an isosceles, then it follows that each pair of base angles is going to be congruent. Okay, so in our example, since we know it's an isosceles, it tells us in the problem and it shows us on the picture. It tells me that my base angles are going to be congruent. So my base 1, both these are going to be the same. My base 2, both of these are going to be the same as well. Alright, so my B1 measure of angle K would be equal to the other base angle of measure of angle L. So if I write that out, that means measure of angle K is going to be 85 degrees. My next one tells me measure of angle M. Well, M is now on this other side. Okay, we have to think back. Okay, this isn't just what we learned on trapezoids. Think about what we've learned about our quadrilaterals, but actually more specifically what we've learned about parallel lines and transversals. Okay, so here if we think about this as a parallel line with a transversal, we have this set of parallel lines that it already has marked. If this is my transversal, that would mean that the angle that I know, this 85 here, is the same side interior as angle M down here. Okay? Same side interior angles, those consecutive angles inside, they are always supplementary. Okay? So that would mean that angle M, if I were to add them up, so I do the measure of angle M plus I add the measure of angle L, they would equal 180 degrees. They're supplementary. So all I have to do is substitute and solve. So I have 180, measure of angle M. So I subtract, and so I get the measure of angle M is equal to 95 degrees. And then the last one it asked me for is measure of angle J. So my measure of angle J is another base angle. Remember earlier we marked these with the same amount of marks because measure of angle J is the same as the other base angle. So if M is 95, that means J is going to be 95. Just like we were just looking at before of mid-segments with triangles, we can also do mid-segments with trapezoids. And so a mid-segment, it works the same way. Think about a mid-segment in a triangle connected to the midpoints of two sides or two legs of our triangle. So the mid-segment of a trapezoid is going to connect the two midpoints between the two legs of our trapezoid, okay, the sides that are not parallel with each other. So some different things happen with this. When this happens, first off, it's going to be parallel automatically with the parallel sides. Okay, we already have that. We have that one set of parallel sides, so that mid-segment is going to be parallel with them as well. And then also we can calculate, just like we did with our triangles, we can calculate our mid-segment by doing half both of the bases added together. So again, like I did earlier, if I call AB is one of my parallel sides, if I say that's B1, and DC is my other parallel side, I'm going to call it B2. This formula is 1/2 base 1 plus base 2. If you think back to a triangle, okay, remember a triangle, we had our mid-segment, and we said the mid-segment was half that base, so if we called this our base 1, and we wanted to calculate our mid-segment would be half the base 1. And the reason that these both work out is because think about if we had another base, if we called this thing up here on our triangle base 2, it has a length of 0. So if I plugged in a 0 for base 2, well, I don't need a 0 in my equation, so that's how these are connected. Okay, they're essentially the same equation, but with a trapezoid we have two bases, so we add them up and we do half of them. Basically we're going to average them out, and that will give us that mid-segment length. So let's go ahead and put this to use. So in this example we have MN is the mid-segment. We can see that even if they hadn't mentioned it in our problem, we can see it because we have these tick marks. So that tells me that M is the midpoint there of PS. And we have these two tick marks on the other side, so that means N is the midpoint of QR. And so to find our mid-segment length, we're going to use the formula. So when I do that, my mid-segment is going to equal half base 1 plus base 2. Okay, so in this case, my mid-segment's Mn is going to equal half. My base 1 is, you can label them either way. It's going to give you the same answer either way. So if I want to call my base 1 the one at the top, then I would do PQ plus base 2 is my SR. And so I'm going to plug those in. So Mn is equal to half. PQ is 12. SR is 28. So if I add those together, I get half 40. And then half of 40 is going to give me 20. So Mn is going to equal 20. And I'm just going to write that in. Mn is equal to 20. So we've gone through some different things. We had parallelograms. Okay, first we talked about quadrilaterals. We know quadrilaterals are four-sided figures. Then we had parallelograms where we had both sides were going to be parallel with each other, both sets of sides. We did trapezoids where we had one pair of sides. And now we have kites. Kites are not parallel. They have no parallel sides at all. Okay, but they have two pairs of consecutive congruent sides. Okay, consecutive congruent sides. Consecutive meaning they're right next to each other. Okay, they're not across from each other like parallelograms. They're right next to each other. And then they're going to be congruent. Okay, consecutive congruent sides. So when we look at a kite, okay, and we typically think of what a kite looks like, the typical kites. So in this picture we have a kite. Our diagonals theorem first, kite diagonals theorem, is going to tell us that its diagonals are going to be perpendicular. Okay, not only are they going to connect those opposite vertices, but our diagonals are going to be perpendicular with each other. And then our opposite angles theorem, kite's opposite angles theorem, is going to tell us that we have one pair of opposite angles that are congruent. Okay, notice it says 1. Okay, it's not 2 or 3 or 4 or 5 or whatnot. It's one pair of opposite angles that are congruent. And it's going to be that pair of angles that connects the two sides that are not the same length. Okay, it's not between your consecutive congruent sides. It's the opposite angles that are between our two different tick mark lengths. Okay, it's that pair of angles. Those are going to be the opposite congruent angles. So if we look at this example, we have a kite and it wants us to find the angle measures. Okay, well we're given two angle measures. And so if I'm looking at this kite, I'm going to kind of outline it here so we can see it a little better. Okay, I have one tick mark here, one tick mark there. I have 2 here and 2 here. Okay, so my consecutive congruent sides, I have these consecutive congruent ones, and I have these consecutive congruent sides, right? Okay, so I said the angle measures, they're opposite of each other, and they're going to be the ones that connect the consecutive sides that are not the same length. Okay, so these two angle measurements that we were given, they're connecting the consecutive congruent sides. I want the consecutive not congruent sides. Those are going to be my opposite ones. So it's going to be these ones that go across here. So I can put there's one line on both of those because they're going to be equal. And so then we have to figure out what is the actual measure of those angles. Okay, well this is a quadrilateral. Okay, in quadrilaterals we can use our formula to find the sum of the interior angles. So going back a little bit to the beginning of chapter 7, we have sum of interior angles is equal to 180 times n minus 2, n being the number of sides. So the sum of our interior angles in this case, we have 180 times the number of sides. It's a quadrilateral, so it's 4-sided. So we have 4 minus 2. So I have 180 times 2, and so that gives me 360. And so to solve this, I have my two unknown angles, but I know they're the same length. So I can essentially do this where I'm going to do 2x. So if I were to term these both as an x, I would term them as the same variable because they're the same size. So I would have 2x plus 115 plus 73 would equal that interior sum of 360. Then I just have to solve. So 115 plus 73 is going to give me 188 So I have 2x plus 188 gives me 360. I subtract to solve. So I'm just going to write it over here. So 2x would then equal 172. I divide by 2, and so I get x is equal to 86. So 86 was in for my x. That means the measure of angle D is equal to 86 degrees. If they asked for the measure of angle F as well, then it would also be 86. They were the same size. And so last thing on here, I'm not going to talk too much about it. It's just our quadrilateral. It's kind of a chart that shows you how they work. So we have the big overlying umbrella of quadrilaterals. We have all these different types that it kind of shows in there. Then we have different branches underneath that. So we have parallelograms, and then we have trapezoids, and we have kites. We have kites that are not trapezoids. We have kites that are not parallelograms. They're all separate groups, but they are all quadrilaterals. Okay, then we go down from there. Kites just stop where they're kites. We have parallelograms branch off into more. They have rectangles and rhombuses, and then those two can go down to be a square as well. And trapezoids can break down to be isosceles trapezoids. Okay, so this is something you need to have it in your notes, and so that way you can refer to it to see what properties apply to what. Because any property that is a quadrilateral property will apply to everything underneath. Okay, but properties that apply to squares will not apply necessarily to all quadrilaterals, right? Squares are all four sides are the same size, and they're parallel with each other, and then they're all going to have right angles. Okay, that doesn't apply to all quadrilaterals, especially because that doesn't apply to kites, and that doesn't apply to trapezoids. Okay.